this video we're going to look at quadratic functions. So to start off, we've already seen that a quadratic function has this form ax squared plus bx plus c. We've been dealing with these about factorizing, simplifying, etc. And we've said that this a cannot be 0. If a is 0, it's no longer quadratic, it's linear. The simplest type of quadratic is y equals x squared. If we plotted all of its values, so we start at 0 and we go up and down, and we go, we'll just square all these numbers. 1 squared is 1, 2 squared is 2, 2 squared is 4, so on and so forth. If we plotted these points, we would see that it creates what we call a parabola. So a parabola is the name of this shape. So anything that has this sort of symmetrical, think of it as like the mouth of a smiley face, if I was to put little eyes in it, the parabola. And we can use this smiley face analogy a bit later on when we talk about positive and negative quadratics as well. So this is a parabola. If you want to have a bit of a read of this, this talks about where it comes from. It's really quite interesting. The higher level maths talks about these things called conic sections. But we see parabolas everywhere. We've seen it in water fountains, bridges, satellite dishes use parabolas. We're even going to look at a thing with bottle rockets. So we'll see that the path that a projectile travels is a parabolic path. So links to our projectile topic, missiles follow parabolic paths. That's why we're looking at it. Some key terminology. We've already talked about parabolas, but if we consider this curved line, this symmetrical curved line is our parabola, there are a few keywords that we need to know and understand in terms of the parabola. The first one is the vertex. And the vertex is sort of, we can think of it as the turning point. So if you think of it as this way, if we're going left to right, the graph is going down, 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 down. It's getting to this point, and now it turns back up. So you could refer to it as a minimum. However, we could also have a parabola that looks like this. And if this is your vertex, this is now a maximum. So it could be a maximum or minimum. So in order to generalize it, we call it the vertex. You can also call it the turning point, but vertex is the official definition for that, rather than turning point. So vertex. We also then have max and min, depending on the type of graph. So in this case, we have a minimum. If we had the other option, we would have a max. We also have concave and convex looking graphs. So we can have a graph like this, so our sad face, we would say that's concave. And we can have a graph that looks like this, which we would say is convex. Now, the easy way to remember between cave and vex, concave looks like a little cave. So if you're hiding in a cave, you would draw it like this. Convex is just the opposite. So it looks kind of like the smiley face. If you can come up with a better way to think of it, by all means use it. But always remember that caves look like this. So concave is that shape. In this example here, we've got a convex quadratic at this point. The vertical line that passes through the vertex. So at the point of the vertex, if we created a vertical line running straight up, we would call that the axis of symmetry. And the reason that we call it that is because if we were to fold this picture along that line, it would be identical. That's the point that we've mirrored. So it's the mirror on either side of the axis of symmetry. And this axis is always going to be running through the vertex. If we draw a line over here, clearly that's not symmetrical. If I fold it in half, I'm not going to have symmetry. So the axis of symmetry always runs through here. So the shape is the parabola, turning point is the vertex, axis of symmetry is that vertical line mirroring it. We also have, and I'm sure we'll talk about this very soon, we have intercepts. So notice we've got an x-intercept and an x-intercept, and we also have a y-intercept here. We talked about intercepts of lines in our previous topic when we looked at linear equations, but this actually links to what we've been doing so far. So everything we've done so far, we've said like solve the quadratic like x plus 1, x minus 3 equals 0. And hopefully using the null factor law, you can immediately say x equals minus 1 and plus 3. But this is actually really powerful. So what you probably haven't realized up until now is that when you're solving for x, you are finding the x-intercepts. These are the points at which this quadratic touches the lines. We haven't done it for quadratic specifically, but we could also say, well, if this is y equals, then if x equals 0 and x equals 0, what does y equal? And then that gives me my y-intercept. So solving these quadratics for x and y is now finding the intercepts. And that's what we're going to look at in this lesson. Let's consider a worked example. So for part A, we want to find the axis intercepts and only using those sketch the graphs. So we're not going to know the exact shape. We're not going to know if it kind of looks like this or if it looks like this. That's going to be a bit tricky to tell. We can just do our best. So I'm going to go through A step by step and then I'll reveal the solution. But intercepts means first we want to solve for x. That's going to be the first step. Solve for x. This is where all the stuff we've done before is really helpful. This tells us that if we're solving for x, that tells you that y equals 0. So that's really crucial. Then using the null factor law, that means that x plus 3 equals 0. And it also means 2 lots of x minus 1 equals 0. So we've got these two solutions here. Therefore, we can say x equals minus 3 and x equals 1. Now in terms of my y, if I want the y-intercept, that tells you that x equals 0, which means if x equals 0, you've got y equals 2 lots of 0 plus 3, 0 minus 1. So that's just 2 lots of 3 minus 1. Minus 1 times 3 is minus 3, minus 6. So y equals minus 6. So we now know y is minus 6, x is here. If I drew my Cartesian plane, I've got, let's go 1, 1, 2, 3, 3, 1, 2, 3, 4, 5, 6. So I've got plus 1 here, minus 3 here, and negative 6 here. I need to kind of draw a symmetrical function that looks like that. So it's going to look something like, I've drawn it very poorly, but you get the idea. There's a bit of artistic skill required in this to draw. So draw a symmetrical function that passes through those points. Remember, it needs to be symmetrical, so that's the hardest part about drawing it. But for something like this, there's certainly a level of forgiveness in how you do it. So let's take a look at the solution. So as you can see, we had 1 and minus 3. And therefore, we also had our minus 6, so they drew it a bit better than I did. We've got this symmetry, the axis of symmetry we can see. Axis of symmetry we can see would be here, and that would be the vertex at that point, which we'll talk about later how we find that. For the next two, it's the same process. You can see they're just solving for x, which is what we've done so far, but then find the y-intercept, use that to draw the graph. In this case, if we've got 1 and 2 and a negative 4, hopefully you can see that if I have these points, it's not possible to draw a happy face, to draw a convex graph. I'll show you what I mean. If I have my Cartesian plane and I've got an intercept here, and the y-intercept's down here, there's no possible way to draw a quadratic that's smiling, because it would have to look something crazy like that, and that's definitely not symmetrical. So the only way to do it is that it intercepts as it's coming up, hits that point, curves, comes back down. That's supposed to touch that. So we can use this information to work out whether it's going to be concave or convex. Let's do some practice now. So for this, let's just do all of one, because these shouldn't take too long and this is really good practice. And state the equation of the axis of symmetry. Let's do that. Axis of symmetry equation. Actually, no, let's leave that for now. Leave question 2, because we will talk about a better way to do that later. And then match the quadratic to the corresponding graph. Let's just do this vertical A, D, and G. So hopefully it should be pretty quick to spot. For example, in A, you would look at this and go, all right, we're going to have 1 and 4. So definitely 1 and 4. They're all 1 and 4. Bugger, that's not useful. What about if x is 0? So we're going to have -1, -4. So that's +4 times 2 is 8. So where do I have an 8? This one. So this one would be C. So follow that process. And in fact, you know what? That's actually pretty easy. Let's do a couple more. So have a go at that. Solutions will be up in just a moment. And here they are. So this is the solutions for 1 up to F and 2 to F, plus solutions for 3 onwards. So that's it for this lesson.